Washington, D.C. You ever notice how D.C. looks like it was drawn with a ruler having a caffeine rush? That's because it kind of was. Back in 1791, French-born engineer Pierre L'Enfant designed the capital as a mathematical symbol of power. He used radial geometry, broad avenues shooting from circles like sunbeams. Each spoke aimed straight at the White House, Capitol, or monument, turning the city into a literal diagram of authority. The logic was political, not just pretty. L'Enfant wanted no single center of power, so the axes intersect instead of stacking hierarchies. The Capitol sits at the city's balance point, 160 feet above sea level, with sightlines linking every major landmark. Hidden math defined everything: the 400-foot-wide National Mall, streets meeting at 30 and 45-degree angles, and the Potomac River's curve used as a natural boundary. Even the distance from the Capitol to the White House, about 1.2 miles, was chosen for symbolic proportion. Wide enough for grandeur, close enough for cohesion. The outcome? D.C. feels ceremonial yet efficient. Resentment and pride share the same grid. Those circles, DuPont, Logan, Thomas, aren't random traffic nightmares. They're nodes placed by 18th century geometry to break monotony and guide sightlines. Over 2 centuries later, the city still runs on that geometry. New skyscrapers can't exceed the Capitol dome's height, preserving the exact perspective L'Enfant imagined. Tourists might just see pretty symmetry, but underneath is a living equation about balance, democracy, and visibility, all calculated long before Google Maps existed. Paris, the golden ratio city. When you walk through Paris and wonder why everything feels perfectly balanced, that's not coincidence, it's math-wearing perfume. In the mid-1800s, Emperor Napoleon III hired Baron George Haussmann to redesign a crowded medieval maze into a modern masterpiece. Between 1853 and 1870, Haussmann leveled 60% of Old Paris, laying over 80 kilometers of boulevards that follow geometric proportion instead of random chance. Each street, park, and facade echoed the golden ratio, roughly 1 to 1.6, a proportion nature uses for balance and our brains read as beauty. Boulevard widths matched building heights, so sunlight hit every floor at the same angle. Corners were trimmed into uniform curves. Intersections spread like spokes from monuments, so vistas always ended in something iconic: the Arc de Triomphe, the Opera Garnier, the Isle de la Cité. Even sewer tunnels were mapped mathematically to slope exactly 1 millimeter per meter, gravity by design. The reason wasn't just looks. Wider boulevards cut disease by improving airflow and stopped barricades during revolts, form meeting control. By 1870, Paris's population had doubled, but traffic flowed, water drained, and real estate boomed. That blueprint still shapes life today. 20 arrondissements spiraling clockwise, radiating symmetry from the Seine. Every cafe terrace, every aligned balcony follows hidden equations for light and livability. Haussmann's math didn't just rebuild a city, it rewrote how the world defines romantic. Paris feels eternal because it's been engineered to be perfectly proportioned since the day it was redrawn. Amsterdam, the fractal of flow. Look at Amsterdam from above and it feels like a seashell drawn by an engineer. The city literally grew in concentric arcs. In the early 1600s, while most of Europe built walls, Amsterdam built canals. The plan, called the Grachtengordel, or Canal Belt, was a perfect mix of math and necessity. As trade exploded, the city expanded outward like ripples on water, each ring calculated for defense, drainage, and delivery. Those 4 main canals, Herengracht, Keizersgracht, the Prinsengracht, and Singel, weren't random. They were drawn by surveyors using geometric progression. Each curve mirrored the last, spacing homes so every merchant had water access without flooding neighbors. The city's 90 islands and 1,500 bridges formed a self-balancing system centuries before spreadsheets existed. Streets met water at right angles to pull tides evenly. Block sizes followed repeating ratios, early fractal logic, keeping the city stable as it grew. And it worked. Ships could sail directly to warehouses, waste and stormwater flowed out instead of stagnating. By 1700, Amsterdam was Europe's busiest port, cleanest capital, and richest per square kilometer. The legacy still flows today. Modern maps trace nearly the same circular geometry. The same proportions regulate bike lanes, tram lines, and even tree placement along canals. So when people call Amsterdam charming, they're really admiring a 400-year-old equation that turned engineering into beauty. A living proof that symmetry and flow can make a city breathe as naturally as water itself. Barcelona, the modular miracle. If geometry ever built a city, it would look like Barcelona. In the mid-1800s, engineer Ildefons Cerdà stared at this cramped, walled city and decided to rewrite it with math. He designed the Eixample, Catalan for extension, a perfect modular grid of 113-meter blocks, each trimmed into 45-degree chamfered corners. Why the cut edges? Efficiency. It let horse carriages and later cars turn smoothly, improved visibility, and created 8 corner plazas at every intersection, tiny lungs of open space woven into stone. Cerdà's math aimed for fairness, not flash. Each block measured the same, so light, air, and population density could be shared evenly. Streets were 20 meters, twice older European norms, and avenues hit 50 meters to carry sea breezes right through the city. He even calculated maximum walking distances to schools, markets, and factories using average human stride lengths. His plan mapped 500 hectares, enough for 500,000 residents, and perfect grid access to the port. At first, the idea was too modern. Politicians mocked it as a city of boxes. Then, technology caught up. Those same squares later held trams, wiring, and now bike lanes and superblocks built for pedestrians. The math aged like fine architecture. Today, drones looking down on Barcelona capture Cerdà's equations still pulsing. Each block a perfect cell in a living organism. His 19th century formulas made one of the densest cities on Earth still breathable, walkable, and unmistakably human. A city designed by numbers, but felt by people. Right outside Abu Dhabi, in a patch of desert where summer hits 49 degrees Celsius, stands one of the most ambitious math experiments ever built, Masdar City. Launched in 2006, it was the UAE's attempt to code a carbon-neutral metropolis from scratch. No chaos, just algorithms. British architect Norman Foster and a team of MIT engineers mapped every street angle using computational wind modeling. Buildings were rotated a few degrees off the sun's axis, so natural airflow cools courtyards up to 20 degrees Celsius lower than open desert. It's the same physics behind ancient Arab wind towers, but simulated with supercomputers. The plan called for 6 square kilometers, powered by an 87,000-panel solar farm and shaded by a honeycombed terracotta mushgrabia screens. Cars were banned inside. Instead, driverless pods glide under raised streets like moving math problems. Even door placements were calculated to funnel breezes, while walkways stay under 140-meter stretches so nothing feels far in the heat. Then came reality. Global financial crisis cuts shrank budgets. Smart pods proved costly. The dream city slowed from a 50,000-person target to barely 2,000 residents by the 2020s. Yet, the data keep teaching. Masdar became a living lab for solar research, battery storage, and sensor-driven planning copied worldwide. The long-term impact. It rewrote how architects use computation to shape climate-resilient cities. Masdar didn't fail. It just pivoted from utopia to prototype. Proof that even in a desert, good math can bend the wind, if not the market. Kyoto, the ancient equation. Stand on a hill above Kyoto and you can see it instantly, the calm symmetry. That order isn't accidental. It's a 1,200-year-old grid built on math, astronomy, and philosophy. In 794 AD, Emperor Kanmu moved Japan's capital here, modeling it on China's grand city Chang'an, itself designed with cosmic geometry, north-south axes for harmony, cardinal gates for protection, and a square layout symbolizing heaven meeting earth. Kyoto's version covered roughly 4.5 by 5.2 kilometers, divided into 9 main north-south avenues and 8 east-west streets, each crossing like graph paper. The imperial palace anchored the northern end on a higher plane, aligning directly south toward the city gates, a spiritual and political compass. Blocks were sized so that temples, homes, and markets all sat within a 10-minute walk, a centuries-old proof of human-scale planning. Fires, wars, and modernization reshaped Kyoto many times, yet the core geometry endures. Even today, you can still navigate by numeric street names, Ichijo, Nijo, Sanjo, because the pattern never broke. That coded simplicity made the city rebuildable after every disaster and preserved its flow of air, sunlight, and people. The long-term impact reaches beyond Japan. Kyoto's invisible math became a template for balance, how proportion, direction, and symbolism can fuse into daily life. It reminds us that long before data models and smart grids, humans already understood something timeless. Order creates peace when numbers follow nature. Songdo, South Korea, the 21st century blueprint. If most cities evolve by accident, Songdo is one that began as a spreadsheet. Around 2003, South Korea literally built it from the sea, reclaiming 6 square kilometers of tidal flats near Incheon. The goal? A global business hub running entirely on data and design, the world's first ubiquitous city. Every pipe, light, and trash bin was planned before the first resident moved in. Fiber optic lines run beneath every street. Sensors track traffic, temperature, and even waste disposal through a pneumatic network that sucks trash directly to sorting centers. No garbage trucks required. Roads, parks, and towers were plotted using energy flow algorithms, so each block sits within a 12-minute walk of transit and green space. A third of the land is parkland, including a 100-acre central park modeled after NYC's, designed with wind studies that lower local temps by 3 degrees Celsius in summer. By 2020, Songdo housed over 170,000 people and 2,600 companies, managed energy use up to 30% more efficiently than older cities, and recycled nearly everything through automated systems. Critics call it sterile, residents call it calm. Noise pollution is down, commutes short, and streets precisely clean. The bigger story is what it taught, how digital infrastructure and urban planning fuse into one nervous system. Songdo became South Korea's living lab, a test ground inspiring smart city districts from Toronto to Dubai. It proves that when math writes the blueprint, even glass and steel can behave like a coordinated organism. A city literally coded to stay alive. Durban, the ocean equation. Standing on Durban's waterfront, you can feel how the city breathes with rhythm. Half math, half tide. South Africa's busiest port didn't just grow from trade, it was shaped by engineering geometry battling nature. When the British founded Durban in the 1830s, swampy sandbars blocked ships from entering. By the early 1900s, engineers used soundings and tide data to dredge a channel through the baymouth, an exact 12-meter deep, 300-meter wide cut aligned to the Indian Ocean's current angles. The harbor's breakwaters were built with trigonometric modeling decades before computers, redirecting cross currents to self-clean silt naturally. The city's grid climbed inland on 5% gradients, chosen deliberately to drain tropical rainfall fast enough to prevent flooding, yet gentle enough for ox-drawn wagons. Later, as apartheid zoning carved rigid racial boundaries, Durban's invisible geometry became political. The way roads, rail lines, and industrial zones divided communities mirrored the same hard lines drawn on planners' maps. In the 1990s, post-apartheid renewal turned this math toward fairness. Urbanists built the Durban Metro with an integrated catchment model, treating neighborhoods as water basins. Data predicted storm flow, housing density, and transit need all in one formula.
It cut flood risk by nearly 40% while linking distant suburbs back to the port economy. Today, Durban balances old harbor geometry with climate modeling. Rising sea projections shape seawalls, and GIS-based zoning manages one of the fastest urbanizing coastlines in Africa. Behind its surf and skyline is a living equation. Centuries of adjusting angles, gradients, and boundaries so a city of 3 million can survive both the ocean's pull and its own history's currents.